Hello and welcome back. We are going to be doing topic 1.2 today, displacement, velocity, and acceleration. This is a very exciting topic because this is where we begin to get into actually representing motion and actually representing physical phenomena. So let's start with a little key difference between two terms that you may think are the same, distance and displacement. Now, if you remember from scalars and vectors, there's a key difference between scalars and vectors, and that is that vectors have direction. In this case, distance is the scalar represented by the symbol d, and displacement is the vector represented by either change in x or, as we saw, x with an arrow. So with the bathroom example I gave last video, if you were to ask, how do I get to the nearest bathroom? You're asking for displacement because you need both a magnitude and a direction. You need the actual physical distance and you need where to go. But if you were to ask how far is the nearest bathroom, you're just asking for distance. Now the SI unit for both of these is the meter. The imperial equivalent of that would be like the foot, but well, it's closer to a yard, but we don't care about imperial. We're doing metric because it's much better. So a meter, if you have things represented in like kilometers and you're trying to make everything SI, make sure to divide it by 1,000. Now we can kind of show the difference between distance and displacement. If I were to have these two things, so this is a starting and an ending, and I would just go pretty much straight across. Let's say we're starting the same ending, I would take a path like that. For displacement, the only thing that matters is the final position minus the initial position. So displacement is final minus initial. So here, the displacement is some value, and here, it's since we're going from the same distance between these two, the starting point and the end point are the same distance apart. The displacement is the same value in both of these cases. So we're going to call this 1. This is equal to displacement 2. But when we actually look at the path traveled, you can see we're obviously traveling more distance in this case. So distance 1 is less than distance 2, even though the displacements are the same. So let's use a little example here using vectors, something we learned about last time. So if we have this kind of collection of vectors here, and we want to know the total distance traveled and our total displacement, how do we do that? So for distance, we just want the sum of all of the magnitudes of these vectors. So here, obviously, the total magnitude would be 6 meters. If we go and calculate the other magnitudes, just using the Pythagorean theorem, like we will use a lot in this course, we get 6.4 meters. And then if we go over to this other one here, we get 2.23 meters. We're just going to say 2.2. So we add all those together, 6 meters plus 6.4 meters plus 2.2 meters is going to be 14.6 meters. And that is our distance traveled. Now for the displacement, what we want is kind of this resultant vector here. So we're going to add all the vector components together, and then we're going to find the magnitude of that. So we add all the x values together, so we have 5 meters plus 60 meters plus 1 meters we're going to end up with 12 6 meters. So let's just draw that here. And we're also going to need to find an angle because it's a displacement, so we always need a direction. So just going to use the Pythagorean theorem here. 6 squared plus 12 squared, square root that, you're going to end up with 13.4 meters. Now, and that was by square root 6 meters squared plus 12 meters squared. And then, to get this angle theta, we just do the inverse tangent of the opposite over adjacent, which is going to be 6 meters over 12 meters, or 1/2. So once we're going to do that, we're going to find that our angle is 26.6 degrees. So we now have that this displacement is 13.4 meters at 26.6 degrees north of east. So that kind of shows the difference between distance and displacement. Now, let's go on to the next part of this topic, velocity. So with velocity and speed, we're in a similar situation as we were with displacement and distance. Speed, which is what we're used to referring to it as, is the scalar quantity. Velocity is the vector quantity. Like, for example, I may have given this example in the last video, I'm not exactly sure. But if you ask somebody what speed they were driving, they're not going to tell you a velocity. They're not going to tell you, oh, I was driving this fast this way. They're just going to tell you, oh, I was driving 30 miles per hour. That doesn't matter where they were driving. That's just the speed. And then velocity, you need a direction. So the simplest here is a V. I like to do it like kind of a weird cursive V with the symbol showing that it's a vector. And speed, usually just represented by a V without a vector. Or sometimes people represent it with S. I don't really like doing that because it also kind of conflicts with arc length. We know kind of the general idea intuitively of what speed is. Speed is your distance over your time. Now, velocity, on the other hand, is very similar, but it's a vector, so it's not going to be the distance. It's going to be the displacement over time. So if I start here and I go 20 meters and then I go back 10 meters and I do this whole thing in 5 seconds, this is going to be a distance of 30 meters and a displacement of 10 meters. Because displacement, we only care about this here, which is 20 minus 10, which is 10 meters. So our speed is going to be 30 meters over 5 seconds. It's going to be 6 meters per second. That is the unit for speed and velocity. Our velocity, on the other hand, is going to be 10 meters over 5 seconds. It's going to be 2 meters per second east. Now, right now we're putting a large emphasis on the specific direction, but in a lot of problems, you're only going to be seeing these quantities you're going to isolate them kind of in one dimension. So the only two directions that are going to matter is plus or minus. That does not symbolize anything with the magnitude. That just tells you the direction. But for now, we're going to keep using directions like east and west. Now, I'm not going to go too much into problems with showing the differences between these two because I kind of did that with distance and displacement. We're just going to go on to our last quantity, which is going to be acceleration. A lot of people have a misconception about acceleration. A lot of people think to accelerate means to speed up. Now, if you speed up, you are accelerating, but to accelerate at all just means to change your velocity. So, if you're in a car, you press on the brakes, even though you're slowing down, you're changing your velocity. So that would mean you're accelerating. If you press on the gas, you're speeding up, you're changing your velocity, you're accelerating. If you turn the steering wheel and your car stays the exact same speed but changes directions, since you have changed the direction and velocity is a vector, you have changed the velocity and you are accelerating. So, acceleration represented by a lowercase a with a vector is going to be the change in velocity over the change in time. So, now that we have this quantity acceleration, we're going to have to go and make a little kind of disclaimer on our last definition. We said that velocity is displacement over time. But that's only true if this object is not accelerating. If the object is at constant acceleration, this is instead the average velocity. Well, how do we get the instantaneous velocity? Now, the difference between average and instantaneous velocity can also be represented with a car. If you're driving down the highway and you look and you see, oh, I'm driving at 62 miles per hour right now, that is your instantaneous velocity. That's how fast you're driving right then. But if you drive 60 miles in an hour, that means you drove an average velocity of 60 miles per hour. That doesn't mean at every point along the drive you're at 60 miles per hour. So how do we get the instantaneous velocity? So if we have this acceleration here, we're going to rearrange this equation into perhaps a more useful one. So if we have acceleration here, change of velocity, remember change can always be represented as final minus initial. Now if we multiply by time, we get AT. This should be changed in t, but I'm just representing it as t for now, is v minus v naught. Now, if we add v naught to both sides, we get final velocity is initial velocity plus acceleration times time. This is a very useful equation because this shows us how if we're moving for any amount of time and we want to know how fast we're moving after a given amount of time, we just take our initial velocity, add that by the acceleration times the time. Now this only works if the acceleration is constant. However, we are assuming all times in this course that you're making you calculate things out like this, that the acceleration is constant. We don't have to go into non-constant acceleration really much at all during this course. So this equation, very useful. That's going to be it for this video. Next topic is going to be split into multiple videos, and it's going to go over a lot of useful equations. It's representing motion, and we're going to see a lot more ways that we can find all of these quantities, and we can express these quantities in terms of each other. I hope you enjoyed. Please leave any questions you have in the comments, and I'll see you in the next video.